All right. So today I'll talk a little bit about diurnal and seasonal predictability of pressures, envelope pressures at residential buildings. And I'll just start off by kind of placing pressures in context of kind of residential air quality. So start out with a little diagram. We see on the left are two of what we call natural drivers of infiltration. The first is temperature differences across the building wall, which is commonly called stack effect, but it just has to do with the buoyancy differences in the air across the wall. The second is wind pressure or wind effect, which just has to do with the incidence of wind on the envelope and how it affects the pressure distribution on it. As we're moving forward through that, they both manifest themselves a little differently on the building wall. The temperature difference kind of distributes itself vertically along the wall, and there's not a whole lot of directional nature to it. It's pretty stable all the way around the building. Kind of conversely, the wind speed has a lot of directional effects, and it'll pressurize or depressurize depending on which face of the building it's on. And so these kind of pressures in tandem with the leakage characteristics of a home are what influence how much air is moving in and out of the home. And depending on the quality of that air, both indoors and outdoors, it can have a significant effect on health and yeah, how it's experienced by the homeowner. So this study is particularly interested in building out and flushing out the connection between these um, weather-based predictions of these pressures, both stack and wind effect. So we will move forward with that. So two of the kind of foundational models that this is kind of born out of are the Lawrence Berkeley National Lab model and the Alberta infiltration model. Both have been around for a while, and they both have had a pretty significant impact in the standards that are put forth by ASHRAE, particularly the ventilation standards. Basically, what that means is just these kind of models are used to understand how much air is moving in and out of the home. And based on that, if it's too low, the standard dictates that more ventilation in terms of mechanical ventilation need to be installed. And so it's a pretty foundational study, or two models, I should say. Both of them are also using leakage characteristics and pressures. But interestingly enough, the relationship between the weather conditions and the pressures don't have a ton of validation, especially in the field. And there's some assumptions that are made based on the relationships between weather conditions at an airport, and those are then kind of corrected to try and represent what's going on at the home. And the final little limitation of these is that these measurements are typically averaged or generalized over hours, days, or years. And so we know that weather, temperature, and therefore pressures change on a smaller time step than that. So we really wanted to hone in on that. So the objective of this was to kind of twofold. One is to go about trying to validate or compare the theoretical relationships between weather and pressure. And then secondly is trying to shrink the time scale that we're measuring at and trying to get a better understanding of how these change with time. Yeah. So we did measurements in 8 homes, the longest of which we did for just over a year. Yeah, we had various different sizes, heights, and kind of different characteristics within the home. We, yeah, so we had some that had 2 exterior walls, 3 exterior walls. So we wanted to get a general idea of what's going on in kind of single family residences. Yeah. So the measurements that we took, we had temperature measurements inside and out. We also had wind pressure or wind speed measurements and direction, as well as differential pressure measurements at kind of the extremities of the home. So we had 2 at the highest, around the highest point of the home, around the roof line, 1 at the lowest point above grade. And we'll get a better understanding of why those were taken in a little bit. But the main reason for choosing these instruments in particular was trying to get the time step that we were looking at as small as possible, and trying to get a really granular view of what's going on the minute-to-minute basis. So these are some of the calculations that we did to understand a little bit more about the pressures that I touched on previously. This in particular had to do with the stack effect. So we had an observed and predicted stack pressure measurements. The predicted pressures that we took, I'll actually go back to kind of show this house diagram shows we have temperature measurements at each floor of the home. And so for each floor, we were taking, based on the temperature and relative humidity, we were getting a density value. And from that, we were able to calculate the floor pressure, stack pressure. And by combining all of the floors together, we were able to get a representation of what that stack would be. In terms of the observed stack, we did measurements, like I said, at the kind of extremities of the home.
Hey, Tom, I'm not seeing your screen anymore. Are other people seeing it? Am I missing something?
I can still see it.
Okay, I don't know what's okay. I'll try to figure out what's going on with my
Um,
computer.
yeah, I can see it too.
Okay, fine.
Okay.
I'll be quiet.
Yeah. So the observed pressures that we took were differential pressures at the extremities. And by taking, we see in this diagram, when we have our differential pressures at the ceiling, we'll have, in reference to indoors, we'll have a positive pressure because the pressure is higher indoors. And so that indoors minus outdoors will be a positive pressure. But due to the fact that the kind of gradient of pressure within the home is greater than outdoors, we actually see at the floor, we'll have a lower pressure than outdoors. And so in between there, we have some point, which is not always necessarily known, that is a neutral point, and the kind of the difference, since the floor is negative, even though it is a difference, it's kind of the summation of it. The summation of these pressures give kind of the net infiltration and exfiltration force, which is important for understanding how air is going to behave within the home. The second comparison we did was predicted and observed wind pressures. So to start off with the predicted, we kind of began with just a simple dynamic pressure from our Bernoulli's equation, with the wind speed squared rho 1/2 rho v squared. To try and make this a little bit more interpretable and get an understanding of the directionality of the wind, we also determined a coefficient in relation to wind direction. We broke the wind direction into 30-degree bins, and for each pressure tap that we measured at, we took a coefficient to try and understand the directional nature of the wind. In terms of the observed pressures, we took the 2 highest taps because there were within a few inches, probably vertically, we were able to pretty successfully negate the effective stack pressures. And so we wanted to see, given a wind, what is kind of the net pressure, both negative and positive, on the home. All right, and finally, the last thing we did, because the kind of foundational models that we were looking at use wind speed correction factors for trying to understand what was going on at the site. We wanted to see, in our own example, between the sites that we measured and the local, I believe it's Northern Colorado Regional Airport down around Loveland, we wanted to see how close this correction factor could get us to what was being experienced at the site. So what the correction factor basically does is two things. One is to try and correct for any height difference between the measurements. So we have kind of the height of the ceiling or roof line of the house, and then we divide that by the height of the airport measurement, which I think the universal standard is 10 meters. So depending on what these next set of coefficients are, can kind of cancel itself out. But the second thing that it is correcting for is the type of terrain that's being measured. So it's a little arbitrary, but basically you try and decide which class each site or the airport and the site are at and make this calculation that way. So starting off with kind of what we saw on the stack, we ended up seeing really great agreement when we were looking at low wind and heating conditions. And heating conditions, for those who don't know, just basically is when the temperature indoors is greater than or equal to that of outdoors. And under these two conditions, we saw really great agreement. Yeah, I believe it was even without the heating factor, we saw generally errors around like the 10, just above like 10% of the total stack pressure in air. So really great agreement here. Two places where two kind of conditions that we didn't see great agreement in were when we did have prevalence of wind. And this was most likely due to the fact that the incidence of wind didn't affect both the low and the high tap equally, because we know that wind is slower due to friction and other obstacles lower to the ground. It'll more times than not have a higher wind speed reported and higher pressurization on the top tap than the lower tap. So it just introduced kind of a piece of pressure that can't be fully explained by just the theoretical stack pressure. And the second condition that we saw some deviation was during cooling conditions. So this is opposite of heating. This is when indoors is cooler than outdoors, typically during the summer if you're running AC or another way keeping your home cooler. We saw as soon as we crossed zero, we saw some deviation from what would be expected just based on stack. And we don't have a great idea of what this could be due to. We kind of, obviously, given the measurement of temperature in each floor, we kind of corrected for as much as we could the stratification. And as you can see kind of in this figure, wind doesn't seem to be the main factor in this. So this is something that definitely needs some more looking at, some more measurements. So now moving on to kind of actually numbers. This is kind of a lot, but basically this is for every site. We sketched out what the dates that we observed over. In terms of the total stack pressure, I initially had set it as average stack pressure, but because especially for site 101, we were looking at over a year, to take just an average of what the stack was doesn't give as much of a nuanced picture. So we took the 9th and 10th and 90th percentile of the stack pressure to get an idea of, okay, what's happening when we're getting down towards cooling, or if we're getting down towards cooling, and then what's the upper bounds of kind of the most potent stack pressures. In terms of the kind of statistics that we did, we started off with a mean absolute error calculation, which just takes for each point the absolute difference between the observed and predicted stack pressures. And we did that for the three conditions, for three conditions. First, just for all observations, second for just for the low wind observations. And right next to those values are kind of the percent of observations in which of the observations was low wind. And finally, both low wind and heating. So we can see in this graph, really only 2 or 3 of the sites had significant cooling conditions. The last 4 or so didn't really experience much cooling events, as these were more into the late fall and kind of winter times, which is to be expected. But within the homes that were experiencing cooling, we did see a fairly significant decrease in our air when we accounted for both low wind and heating. But it did appear that low wind seemed to be the biggest improvement in terms of when we were filtering out what observations were creating the most error. Once we accounted for that, it was much better. So I'll move into wind predictions now. In terms of the predicted and observed wind pressures, we saw not as good of predictions as we did in STAC, and this is mostly due to the fact of the just kind of noisiness of the measurements, but also in terms of the magnitude of these predictions. They seem to be under predictive when we were taking our dynamic wind pressures. We also saw it at times in multiple sites. We saw kind of a maintained pressurization during wind events, kind of in the midst of wind events, even though at times the wind was dropping to 0. I'm looking in particular kind of at just before midnight on November 24th. We see kind of a maintained pressurization, even though the wind speed seems to be dropping to 0. And so our contribution of wind would be assumed to be 0. Keep this. In terms of trying to account for the directionality of wind, we were taking each tap and dividing, I talked about earlier, dividing the directionality into 30-degree bins, which we see on the wind direction column. And for that, we were taking a linear regression between the pressures and the predicted 1/2 rho v squared estimates. So this was kind of an extreme example. There were kind of a table for every one of the sites, but this showed kind of 2 of the unexpected characteristics that we saw in quite a few of the other sites. The first being that even across a various number of wind directions, we didn't see too much or a very consistent crossover between signs, which we would expect. As we, for example, if we have a direction that's directly facing the tap, that we would expect that that tap would be pressurized and therefore positive. But conversely, if it was on the opposite side of the building, we would expect a negative in this case. So that was one of the things that was a little interesting about these points. The second thing was, particularly for the high taps, there seemed to be a similar sign and kind of magnitude for a given angle, which we also wouldn't expect for kind of the same reasons as the last time. When we have wind on a face, we would expect to see positive pressurization and the opposite for if it's on the opposite side of the building. But this wasn't for all sites, but it was just a source of kind of inconsistency that we've seen in some of them. So to try and get just a general relationship between wind speed and observed pressurization, instead of trying to do point predictions, which because of the noisiness and kind of inconsistent coefficients, we decided to try and just look at for a given wind speed, or a wind speed squared, can we get an idea of what that kind of pressurization would look like. So this was an example of a good one. I think the R squared of this one was around 60 point or 0.6. And so it wasn't necessarily good for all of them, and I'll show an example. So for some of them, especially in the sites that we didn't see a ton of high wind observations, the corresponding pressure to wind speed didn't seem to have a very linear relationship. And so we had some that particularly 229 and 227 that showed actually decent linear relationship, but for the vast majority of the other ones, it didn't seem to really correlate. And now I want to look at the relationship between site weather conditions and airport weather conditions. Like we said before, a lot of the preeminent models use corrections for airport wind speed. And so we wanted to see how well does airport wind speed represent conditions that we're seeing at the site. So first thing right off the bat we notice is the kind of granularity of the data is a whole lot different. The airport, generally airports measure around hourly, once an hour measurements, which is very different from kind of the 1 or 5 minute measurements that we were taking at our site. Secondly, the magnitude is pretty significantly different especially at kind of the highest peaks of wind events. We're seeing somewhere around 5 times greater wind speeds, and likely due to mostly the difference in height. But we'll touch on that and kind of the correction for that and see if it makes a difference in a second here. But lastly is looking at kind of a wind rose. At the top wind rose, we see the general direction that we recorded at site, and the lower wind rose is what was measured at the airport. This could be partially skewed by the placement of the weather station at the site, having to do with shielding from other buildings or things. As much as that was limited, there was unavoidable obstacles in that sense. But overall, I think it does paint a picture that there doesn't seem to be a ton of relationship between kind of the wind that's being observed at the airport and the site. So to try and make it a little bit more similar, we used the correction factor we talked about earlier. That was developed by the Lawrence Berkeley National Lab. So the first graph is at site 227. We see, similar to what we saw earlier, kind of a 4 to 5 times greater value in wind speed at the airport compared to the site. And the second graph is what it looked like after correcting. Now, part of this is when looking at those correction factors, the ability of the correction factor to kind of do its job really depends on the person choosing the right classification for what each site kind of is. There's 5 classifications that ranges from like open ocean with no obstacles within like 5 kilometers or 3 miles or so. And then classification 5 is like the middle of Manhattan or some like very urban, lots of skyscrapers, lots of obstacles. But I think part of what this shows is, one, it doesn't do an amazing job in and of itself. And secondly, kind of the arbitrariness of having to decide those classifications makes it just not necessarily ideal for making assumptions of what the conditions are on site. All right, so kind of to clean up here, we saw within stack pressure, we saw an excellent agreement, particularly under low wind and heating conditions. We saw for both low wind and heating, we saw around 10% error or less for most sites. In terms of wind events, one of the things we are able to say is that when we were recording wind signals, it was a great, excellent indication that there was pressurization going to be happening on the house. in terms of the actual relationship between pressures and wind speed, we had mixed results in terms of kind of the scatter plots we talked about earlier. And in terms of point predictions, just because of noise and the coefficients that didn't necessarily line up with expectations, they didn't seem reliable to try and make point by point predictions and kind of MAE values as we did with stack. And then airport speed was significantly different in both granularity and magnitude. And even with the correction, it still was roughly 3 times greater than what we were witnessing on site. So I'll wrap up a little bit with kind of what this adds to the air quality field. One, going back to the objectives, was trying to get a high resolution prediction, both to better understand the dynamics of airflow on that timescale, and also to for the potential to actively manage kind of the way that air is moving in and around the house. And kind of finally is the further and more in-depth validation or comparison of theoretical relations between weather and pressure. Yeah. All right, so I will look at chat now. If anyone wants to chime up, feel free, but no.
It's 27 minutes.
Okay. Well, there's more to add anyway. I know of at least there were some R-squared values I want to throw in there, and some the wind speed cutoff I didn't go into, so I those are at least a few minutes. Let's see.
So I have a lot of time to work with Dom offline, so I'd like to spend the rest of the time getting thoughts from people. And Dom, I think you'll find that people don't understand different things, and
Yeah.
sometimes they're interesting and useful in preparing for an audience. So everyone go ahead and ask your questions. And Dom, you probably saw that Ellison has questions in the chat. I am taking
Yes.
notes, and I will be saving the chat, so you don't have to do that.
Perfect. So I'll start with Ellison. General question: what sort of data cleaning do you for these site data sets? Do you have any? Yes. So in terms of data cleaning, we did. There was kind of 2 main ones that are coming to mind now. One was kind of smoothing of it a lot, especially with the both stack and wind observed pressures. There's a lot of kind of sporadic nature in the data, and so kind of I think we used 15 minutes or so smoothing for each, just especially for just visual kind of representations of it and getting an idea of what's going on. The other thing was there were times where measurement tools kind of cut out or had kind of flat lines that were kind of unexplainable. And so that was another source of cleaning. Exclusionary criteria, not necessarily exclusionary. I think in terms of the filtering, there was some decisions made on like where the wind speed cutoffs. So when we were doing the general understanding of what the baseline stack pressures were, we wanted to pick a number and filter out all the wind speeds above that number. And so it wasn't necessarily excluded, but in terms of trying to get a better understanding of what those kind of conditions that best represent the stack, we did do that.
So Dom, and by the way, this is also an exercise in answering questions. I believe Ellison's main question is, did we throw away any data?
Yes, I think the only thrown away data was the kind of flatlined or zeroed out dead loggers that we logging data that we had. That was the only one that I can think of that we just kind of tossed.
Okay. Yeah, I was asking the question out of genuine curiosity because you mentioned a number of times how noisy your data are, and it seems like you have used most of it
Mhm.
which has strength. And, maybe thinking for master's thesis defense, you would just want to think of what those strengths are. But I guess one follow-up question, if that's all right, Tammy
Mhm.
or any Dom,
Yeah.
is in thinking about what you like your title and your objective around diurnal and seasonal variability. And I might have missed it, but if you were to subset your regression analysis, or if you were to include in your regression analysis fixed effect variables for things like season or
Mhm.
time of day. I'm not asking that you do this analysis for your presentation, but it might be worth thinking about, like, how do you think that would influence your regression based
Okay.
on, some of the things that you observed? I mean, you can try and answer that now, or maybe store it away. I think there's only about 7 or 10 minutes, so feel free to pass and move on to other people's questions, but something to think
Yeah.
about.
Yeah, totally. For in terms of regressions, I don't have an answer right now, but I do think that would be helpful in kind of, like you said, underlining the diurnal and seasonal influence of it and stuff like that. So yeah, totally making note of that.
I think, Dom, that what you want to think about though is what dependencies are we really claiming? And
hmm,
so are we really claiming a dependence on hour of day, or are we just saying it varies diurnally because weather conditions vary diurnally and we're accounting for those? Same with
yeah,
seasons, right?
yeah,
So a lot of regressions, and I think you may not have seen some of the types of work, but some regressions might just say, we're going to compare this with a categorical variable that's winter and spring.
I see.
And that's
Okay.
not what you're doing. So just be
Hmm.
prepared to clarify that.
Yeah, yeah. Okay. Um, Paul, you said, did you find stack height? No, that was one thing that I did notice as I was going through. The stack height generally has to do with kind of the distance between the lowest above grade point and the kind of the roof line of the home. In this sense, we were just taking that stack height to be between the two taps, the high and low taps. Because we can't really account for or kind of get calculations for anything beyond those points. But yeah, sorry, that definitely is something that should be mentioned. Um, okay, yeah, Paul is the expert on ASHRAE. I have kind of only a very general idea of kind of what the consequences or what the benefits of adhering to ASHRAE standards are. So yeah, provides a credit for infiltration. Okay, interesting. Okay.
Any questions from the communication team or people who might be new to this work? Just don't be shy about feeling like this is not your thing, or you just got here and so you don't, of course you don't understand. Sometimes those are the best questions.
Hi, yeah, I do have a question.
Mhm.
But I thought you did a really great job with the presentation. I thought your pacing was really good.
Thank you.
And yeah, I think the slides had a good balance of like figures and text and enough stuff on it so that it was a good slide, but not too much that it felt overwhelming. So
Yeah, I
that
think
was
the
good.
later ones I had a little too much words, but that it's like I said, very, very rough draft. So yeah, much to
Mhm.
do.
So I
Thank you
did
though.
have a question on, I forget what the axes were, but when you were predicting, and you showed like a scatter plot with that red line, and you said maybe the R squared was around like 0.6. And then, yeah, you were
Yeah.
saying that, okay, so the wind pressure versus the wind speed. So do you have any insight into why some of the sites had a better like R squared than others? Were there
Yeah.
differences? Yeah.
Yeah. I don't have a perfect understanding of it. I do think because this doesn't necessarily take into account kind of directionality, there's some because our obviously our taps are static, depending on where the wind is coming from, it'll have for a given wind speed recorded by the weather station, there might be different kind of pressures observed by those manometers. Other than that, there's the possibility also that there are other other effects in there, namely like mechanical ventilation. And so they could be kind of, because they maybe coincide with a wind speed that maybe is above the threshold of 0.5 meters per second. It then kind of gets conflated. I think those are the only two that I can really think of that would be kind of misconstruing these in this relationship. But yeah.
So, because
So
we're all
these-
friends here, Dom, I'll let you go next, Naomi. Dom, you don't ever want to give an answer that just undermines your entire analysis, which you just did.
Yeah.
Be careful. And
Mhm.
and I think you're punting, but you just killed everything. And we've looked at mechanical ventilation, right? And we know
Mhm.
that it should cancel out in a lot of cases. So
Yeah.
you don't want to give reviewers or an audience a chance to go after your blood.
Right.
Okay, Naomi, you're up again.
Yeah, so I guess the question is like between these sites, are they different? I might have missed this. Are they different buildings or is it like different sites within the building?
Yeah, so completely different buildings. A couple of them are kind of townhouses that may be connected to a different building, but those we didn't do any like side by side or connected buildings in that sense. So yeah, completely different, very different in terms of kind of the orientation, the style, and kind of the size in some cases. So yeah.
Okay, interesting. Thank you.
Yeah, Daniel, I see you.
So kind of building off of Naomi's question, was there any kind of correction between the buildings for HVAC type, like forced air versus radiative versus window unit, something like that?
Yeah, so we did do, it's not too much touched in what I'll be presenting, but we did do measurements of all of the present kind of mechanical ventilations, whether that was bath fans, HVAC, I'm trying to think, hood, range hoods, anything like that. We did do measurements of and got signals for what that would look like on the manometers. But in terms of actually going through and like for each site characterizing, oh, this is, we know that based on this magnitude of pressurization or based on this kind of step function, we know that this is due to this thing. So it was more to kind of get just a general idea of what contribution to pressure those fans or ventilation forms may give, and have an eye out for that kind of visually in the data.
Dom,
Yep.
you're forgetting the delta delta P should cancel all that stuff out.
Yep. Yep.
That's your answer. Okay. All righty. Yes, that stuff is important, Danny, and we'll get into that. And then Marilee's got a question in the chat.
Sure. That's a good question. One thing that I could tell them, I think the main thing that I took away from this, I don't, obviously me not being a homeowner, I don't know that I'm the best example of this, but in terms of when I was first looking at these kind of models and understanding how the different effects kind of combine to get like a general pressure, it kind of seemed just like a true addition or kind of summation relationship where, okay, well, we're always going to have stack and we're always going to have wind, and we just add them together and it'll be hunky-dory. But it certainly seems from what we've seen that stack does seem to be the most dominant form of kind of driving pressure. And although the wind, while still present and in some cases still able to pressurize a significant amount, its effect isn't as kind of widespread or consistent throughout time. So, yeah.
And I think that would be I'm hoping we can pull that out of the data, is the perhaps flow driven by stack versus flow driven by wind
Mhm.
overall. We can estimate that. So maybe translating that to homeowner language would be something like when it's cold outside, your house has more flow through it than even if it's really than caused by even if it's really windy or something like that.
Right.
I want to call out what Paul said about wind.
Mm.
We're just for the team's instruction. I think you've shown here, Don, that and I think we're going to get more into this as we polish the paper. What we see in the wind response of a structure or of a home is completely not what you would expect
Mhm.
based on theory.
Mhm.
And it's not very different that as in there is a response to wind, but all the directionality and the magnitude is not what you would expect. That means the models are wrong. Okay, we knew that.
Mhm.
But also, and I think what Paul might be highlighting is it's made me wonder, there's this thing in the LBNL model about the interior pressure coefficient. That is how the inside of the house is overall responding to that force. That's
Mhm.
kind of buried in all the models. Um, and it's almost a throwaway, but looking at these data, I really don't think it's a throwaway. I think it might be dominating the whole picture. This is something that people don't even think to ask. And so when
Mhm.
Paul says we are getting an idea of what the questions are, it's not just that we're not matching the theory, it's that we were probably asking the wrong question.
Mhm. Yeah.
Anyone
Will,
else?
going off of Naomi's question about the sites and types of homes, is it worth mentioning that homes that um worth mentioning that homes are from different areas in Fort Collins, so not only were they different types of homes, but they are spread out around town. Maybe not important for these reasons. Yeah, I don't know exactly what kind of the actual location of them, unless there was some sort of different either kind of terrain value for that, or if it was kind of more taller buildings or in like a more forested area, it could cause some changes to the way that wind interacts with it. But yeah, I guess I don't know if there was another reason to point out those kind of different spots around Fort Collins. And Paul. Um, so in terms of, in terms of, but
Oh.
I'm curious. I am curious to hear. So harder to reverse it in terms of, uh, in terms of like reversing from flows to like estimations of pressure, or is that kind of what you mean?
All right, so it's noisy here, so I've been staying on mute, but I'm gonna try see if this works, just because I'm not gonna put this in chat. I've seen this with flues. Like if you have a draft established in a water heater flue,
Hmm?
it takes more negative pressure to reverse it than if you turned the thing on that reversed the flow in the first place and then tried to have the water heater establish a draft. It's like once you've established that flow, something has to actually pull on it to reverse it, as opposed to just acting on its own. And so there's a mass and a momentum component. These, I don't know whether this is true, but looking at these data makes me wonder if that kind of an effect is there, which is completely not even considered or thought about in the models, and could be. When I say I think we've got a better idea of some questions. That's a question that I'm wondering, that I've never really wondered before seeing your data.
Mm-hmm. Mm-hmm. Definitely. Yeah, and
So
Erica,
let's
sorry,
close
go.
out with Erica's question because I think it's a good one.
Yeah, yeah. So I would say it's one of it kind of two things that it benefits or kind of influence that it has. I would say one is kind of filling in a gap in the literature in terms of getting a better understand, not necessarily validation, but getting some sort of comparison to see how close the theoretical relationships between weather and pressure are. And then secondly is kind of in relation to our project, kind of opening the door with this smaller timescale measurement, trying to make it mold into, and Tammy, we have talked about it a little bit, but at a certain point, we almost said when we have these pressure observations or measurements, is it even worth it in terms of our integration kind of with our project's HVAC system? Is it worth it to move forward to the estimation of infiltration, or is it enough to even just say, okay, we know due to stack effect and maybe an instance of wind, we're expected this much pressurization, and so that's how much we need to push through the HVAC system to maintain that pressurization and stop infiltration that we don't want. So yeah, those two are the main things.
Yeah, so one of the things I'm going to encourage you to do, Dom, is to identify your scientific questions in the beginning and then place them in the context of the project.
Okay.
Cool.
Awesome.
Okay, Dom, what time is your defense? It is in the powerhouse classroom.
Yep, the main classroom down right by the front door. It's 9 a.m. on August 13th.
Okay, so everyone's invited, and then party at my house afterwards, either to likely to celebrate Dom, and you know, if Dom will probably need a lot of consoling if he has to do it again. So come to my house at any rate, and I'll send out invitations before then. Quick note, I did barely submit the progress report on time, 30 minutes before it was due. Excellent. Thank you all for your help. The document has been updated if you want to take a look at it so you can see what I said about us. Okay, see you next week.
Thanks, everyone. Appreciate it.
Thanks for your comments.